So today we're going to be talking about signal flow graphs and how they can be used to analyze microwave networks. So what is a signal flow graph and why might we want one? Well, if we go back to our basics of microwave engineering, you've got, in general, a two-port network. It's characterized by a set of S parameters. You've got your incoming wave and your outgoing wave on each port, and the circuit is essentially complete. But when you start attaching things to the two-port network, things can get pretty complicated pretty quickly. So say you want to attach a load, ZL. And what if I'm interested in finding the input impedance at this port, Zn? How would I go about doing that? Well, you might want to convert your S parameters into transmission parameters, and then you can do some matrix multiplication, and then when all is said and done, you have the input impedance. But this is really difficult. And so if there were an easier way to get single bits of information that we're interested in, like Z in or gamma in or gamma out, if there were a way to get these pieces of information without having to analyze the entire two-port network, that would be awesome. And that's exactly what signal flow graphs let us do. And they're really interesting because they let us represent linear equations graphically. So they let us represent things that are rather complicated in a rather simple way. So if we're interested in representing this arbitrary two-port network with a signal flow graph, how would we go about it? Well, before we analyze a two-port network, let's just analyze a single one-port network. And what is a one-port network? Well, a one-port network is just a resistor, for example. It's anything that has two terminals. So we're going to analyze this one-port network. Let's say it's got a certain impedance, and we're going to say that there's an incoming wave A and an outgoing wave B. Now, the way that you would analyze this in terms of a signal flow graph is really quite simple. So you've got this node A, and then you travel along this branch, and it's similar nomenclature to circuits analysis, to this other node B. So A and B are your two signals that you're interested in. And then along this branch, you've got a multiplication factor, gamma. So B is nothing but gamma times A. And that's indeed what you'd expect from a transmission line connected to a load, for example. So if you've got just your standard transmission line connected to some load RL, then you expect that if there's an incoming wave, A, or a voltage wave if you prefer, and an outgoing wave B, that B is just equal to gamma times A. And in transmission line theory, we know that gamma is just equal to RL minus Z naught over RL plus Z naught. It's not really important for what we're doing, but just to tie everything together. So, okay, if that's how we represent a one-port network, and I'm assuming that we're on the same page here. So this node, nodes represent the signals that we're interested in, so A and B here, and branches have a certain scalar value associated with them. So here that's a gamma, and they set up relationships between these nodes. So B is equal to gamma times A. And it's very important the direction of which you write a signal flow graph in. If it doesn't have the same direction, it means a completely different thing. So okay, let's move on to calculating our two-port network parameters. So let's redraw it down here. You've got your two-port network. It's characterized by some S parameters. You've got an incoming wave on this side, let's call it A1, an outgoing wave B1. On the other port, you've got an incoming wave A2 and an outgoing wave B2. Now, if we just glance at our above diagram with how we represented a one-port network, we might just say that, well, we want to represent it probably similarly. So let's draw one node here and one node here, A1 and B1. And then we draw a line between them. And what's the relationship between A1 and B1? Well, that's nothing but our S parameters. So we know that B1 is just equal to S11 times A1 plus S12 A2, and B2 is equal to S21 A1 plus S22 A2. And I'm just writing this here for reference as we go through this activity. So we've got an incoming wave A1, an outgoing wave B1, and that's our first port. That's complete. And now if we're interested in drawing our second port, uh, we know that A1 uh, from this equation over here, um, we know that A1 is involved in producing B1 and it's involved in producing B2. So A1, we're going to draw a straight line over to this node B2. And the coefficient for that, if we just look at our S matrix real quick, well, that's S21. And over here, I should write S11 because A1 to B1, just from our S matrix, that coefficient is S11. Okay, now we're just missing one node, A2, and we know that A2 helps to generate B1 with the coefficient. If we just look it up real quick, so B1, A2, that coefficient is S12, and A2 helps to generate B2 with coefficient S22. And I just find it really helpful to keep the S matrix equations present in most of the work that I do, just in case I forget things. So this is an incoming wave, and that is an outgoing wave. So this is our completed two-port network in signal flow form. Now, in the next video, I'm going to talk about the rules for signal flow graphs, but really quickly, I'm going to give you the motivation for those rules and where those rules come from. And I'm assuming that you're fairly familiar with block diagrams. Well, interestingly, signal flow graphs are exactly the same as block diagrams. They're just a different way of representing them. So if we want to draw a block diagram equivalent of our two-port network signal flow graph, it just goes like this. We've got an input signal A1, an output signal B2, and a block in between that scales it appropriately. We've got another input signal down over here, and this is a little strange way of writing it, but just to maintain consistency, we've got a block S22 and our input signal A2. And then A2 also goes over to generate B1, which is, we've got a little summing junction here. And then our output signal B1. And A1 is also used to generate B1 with S11. And that's all signal flow graphs are. They're exactly equivalent to block diagrams. They're just a more convenient way of writing them. So we can use all of the rules that we've established in analyzing block diagrams to analyze signal flow graphs because they are quite literally identical. And so this video was sort of a more theoretical basis for what we are doing next. But in the next video, we're going to go over a couple examples. So how do we calculate quantities like gamma in, for example, from a signal flow graph, and why we might want to. And the reason that I'll show you, the reason we want to use signal flow graphs is because they are so much simpler than analyzing the linear equations, and they're so much more intuitive once you grasp what is actually going on.